My name is Cameron Sanders, and this is my project proposal playlist for optimization methods in engineering. So what is the problem I'm going to be looking at? So the problem to be optimized is that of predicting polymer solution mixing. It's a difficult task to achieve, but is made much simpler through the optimization of conditions favorable to mixing. So predict whether a polymer and a polymer or polymer and a solvent will mix is done using a set number of parameters. So you have your solubility parameter del, your interaction parameter chi, molecular weight of the solvents in the polymers, and the solution mixing temperature, as well as the crystallinity of the polymer. We're going to, however, look at the del, chi, and the molecular weights. So let's expand on those. So your solubility parameter, del, is formed using a number of constants. So you have your density rho, your sum of your molar attraction values, all the product of which is divided by the MER molecular weight. All three of these are constants, so we can treat del as a constant as well. And then we have our interaction parameter, which is variable, which is the product of V, your volume, times the difference between your solubility parameters squared over Boltzmann's times temperature. So we know that increasing temperature of reaction tends to add favorability to mixing, as well as our volume ratio is reflective of the ratio, our volume is reflective of the ratio of polymer to polymer and polymer to solvent, both of which are variable, meaning that our interaction parameter can be used as our optimization criterion. So why is this important? Being able to optimize conditions for mixing can prevent overwork as well as rework, as well as being able to predict optimal conditions for mixing increases the probability of our experimental success. So our plan for finding an optimum and solving this problem is to first determine the miscibility of a set number of polymers that will be used to develop our optimization procedure. So we know that polymers with a similar del tend to favor mixing, so this can be used to compile a set list of polymers as our initial population. The next step using this initial population is determine at which temperature these populations best mix, i.e. maximize our interaction parameter. And then our final step will be to determine which ratios of polymers engender the greatest miscibility. So what will be the significance of solving it? Once an optimization procedure has been established for this task, it can be repeated over and over again for all future mixing experiments, minimizing our possibility of rework or overwork.